This chapter, we are going to explore classification in machine learning. MIST dataset contains 700 handwritten pixel images. This dataset is widely used by many classification algorithms to test their performance. Let's load the data into the memory and check it out. Because this dataset is widely used, lots of common libraries have it. The plot library shows it is 5, and the first row in the y-test is also 5. Instead of directly jumping into multi-values classification, let's start with a simple binary classification. The system only outputs true or false from the given input. Our job is only to detect if the image is 5 or not. In order to do this, we need to modify our dataset. Instead of keeping all the extra numbers, our new y of train and test becomes the value of the true or false. 5 for true and non-5 for false. We can use a stochastic gradient descent classifier as our starting point. We need to convert the shape before feeding into the model. This code converts 28 by 28 2D array into 1 by 784 array. We train it on the train set, and now we can use the model to predict the first two cases from the train set. Remember, we use root mean square error (RMSE) to measure regression model performance. However, measuring the performance of classification algorithms is a little bit tricky. We can use accuracy to measure classification algorithms, but accuracy is not very meaningful. Let me tell you why. Let's check what is a percentage of 5s in our dataset. There are roughly 10%. This means 90% of our data is false. If we have a very bad model, it always outputs false. 90% of the time, our model can give the right answer. The accuracy of the real bad model is 90%. So the accuracy is not a good measurement of the classification model performance. In particular, we shouldn't use it to measure schooled dataset. School data means some classes are more or less than other classes. In our case, 5s are much less than non-5s. I put a cross-validation score and use accuracy to measure our model. You can see the accuracy is a little bit less than 90%. Here's the confusion matrix comes into play. The main idea of confusion matrix is to figure out how many times model misclassifying things. Essentially, we want to find out how many times our model classifies actual 5 to false, and how many times it classifies actual non-5s to true. In order to compute the confusion matrix, we need to get the actual predicted results from the model. Cross-value predict function gives a prediction from the model. It uses threefold cross-validation. Each time, the model uses two-folds for training and one-fold for prediction. Y-train predict contains entire predictions from the stochastic gradient descent classifier. We can use the confusion matrix package and feed the prediction and actual results to get the confusion matrix. Each row in the output means the actual class, and each column means predict class. 53892 means actual non-5s, and the model correctly predicts them as a non-5. They are called true negatives. 687 means actually non-5s, but the model predicts they are as 5. This is called false positives. 1891 means actual 5s, but the model predicts them as non-5s. This is also called false negative. 3530 means actual 5s and the model predicts as 5s. This is called true positive. Let's take a look at this picture for better understanding. The two true parts from top left to the bottom right are the correct predictions. Other two parts are false predictions. Again, true positive stands for model truly predicts positive. True negative stands for model truly predicts negative. For binary classifiers, the perfect model should only have the true positive and true negatives. But in reality, the perfect model doesn't exist. When something goes wrong, there are only two ways. The model wrongly predicted actual negative to positive. This is false positive. The model wrongly predicts actual positive to negative. This is called false negative. From the confusion matrix, we can derive two important concise metrics that directly reflect the performance of a classification model. First, precision. Precision means accuracy of positive predictions. This is a formula to calculate precision. The numerator represents the number of times the model correctly predicts a positive class, while the denominator is the total number of positive predictions made by the model. This includes both correct and incorrect. So precision essentially tells us what percentage of model positive predictions are actually correct. The higher the precision, the more confidence the model is making accurate positive predictions. In the extreme case, if our model only makes one positive prediction and ensures it is correct, our model has a 100% precision. But 100% precision doesn't necessarily mean the classifier is perfect. Here we need a second matrix, recall, the ability to identify all positive instances. This is a formula to calculate recall. The numerator is a model that correctly predicts the positive instance. The denominator is truly predicted positive plus false predicted negative. In other words, the total number of actual positive instances in a dataset. The recall essentially tells us the ratio of positive instances that are correctly detected by the classifier. The higher recall means the model is better to identify more positives. Let's get back to our 5 classifier and check the position and recall. We can use a number from the previous result of confusion matrix and plug into the formula, like the commented code, but sklearn has functions to simplify this. The precision number tells the classifier is correctly 83% of time. The recall number tells the classifier only detects 65% of 5s. We always want to have a classifier with high precision and high recall. This means when a model predicts a positive, it is more likely the prediction is correct. At the same time, the model can identify most of the positive from the dataset. But in reality, this kind of model does not really exist. We need to make some trade-off for precision and recall based on what we think is more important. Let's say we build a classifier to identify video good for kids. Positive means good for kids, and negative means not good for kids. This model should focus on precision. When the classifier says the video is good for kids, the video should be good for kids in reality. And we don't need a classifier to identify all the good videos for kids. So the precision is more important than recall. For another example, we need a classifier to find all defect parts in a production line. Positive means product is defected, and negative means product is good. The classifier should identify as many as defects as possible, but accuracy of identifying those defects is less important. In this example, recall is more important than precision. We can use threshold to adjust precision and recall. This is a picture from the book. When the threshold is larger, the model has more accurate prediction on 5s, but only identifies a few 5s. It has large precision, but small recall. When the threshold is smaller, the model has less accurate predictions on 5s, but it can identify more 5s. It has small precision, but large recall. Let's get back to the code. SDG classifier makes its classification decision based on the score calculated by the decision function. If the score is bigger than the threshold, the instance is classified as positive. Otherwise, the instance is classified as negative. We use decision function to access a score. If you remember, the first train data is 5. The decision function returns 2164. SDG classifier uses a threshold equals to 0. Internally, it compares 2164 with 0, and the result is larger than 0. So the output is true. If we raise the threshold to 3000, this input will result as false. If we use 3000 as a threshold, we essentially ask the model to become more precise, but it hurts recall. If we want to find the right balance based on the different scenarios, how do we find the right threshold we should use? Let's visualize the precision and recall curve. This decision function parameter can give us all the decision score from each cross-validation fold of X train. Precision recall curve uses all different thresholds and calculates corresponding precision and recall from the model. Small threshold gives a good recall but bad precision, vice versa. You may notice the precision curve is bumpier than the recall curve. Let's use the previous example to explain. When the threshold is at the middle, we calculate precision by 4 divided by 5, 80%. When we move the threshold right a little bit, now the precision is 3 over 4, 75%. This explains why, increasing the threshold, the precision sometimes drops. Regarding how to choose a threshold, it usually depends on what exactly you want. Let's say we want a higher precision. We want 95% of 5 predictions to be right. Let's find out what threshold we should use. The NumPy argmax returns the first index in the precision array whose value is larger than 0.95. From a result, we need to set our threshold as 10,480 in order to achieve 95% precision. Let's check the recall. The recall is only around 20%. Again, our classifier with high threshold detects 20% of 5s from the entire training set, and 95% of 5s predicted by the model are correct. And this wraps up the first part of Chapter 3. The confusion matrix seems a little bit confusing at the first glance, but don't worry, rewind the video a couple of times and it will start to make perfect sense. This topic is absolutely crucial for understanding classification algorithms. It lays the foundation for evaluating model performance and help us to benchmark how well the classifier's model is. I hope you find this video helpful. If you did, please give a thumb up and consider subscribing to this channel. Thanks for watching, and I will see you in the next video.